Hi, I want to talk to you about one of the fundamental RL algorithms, the reinforce policy gradient algorithm. Reinforce is foundational to many RL algorithms such as actor critic, PPO, RLHF, and other modern policy gradient methods. Today, I want to do a deep dive into the reinforce algorithm from first principles leading up to a PyTorch implementation. Here's a rough outline. Let's start with the high-level idea followed by algorithm highlights such as policy network, action sampling, policy update, and the main loop. We'll then talk about pros and cons of reinforce and ways to improve it. Finally, we'll conclude with a PyTorch implementation of the algorithm in a simple RL gym environment. Reinforce is one of the simplest RL algorithms. It directly learns the policy by increasing the probability of actions that lead to high rewards. Policy is a way of acting in an environment. It's a probability of taking a particular action given a certain state. In our case, we represent the policy by a neural network that takes in the state as the input and outputs action probabilities as the output. When we interact with the environment, we receive a reward and a new state. Our objective is to maximize the cumulative reward. We may also choose to discount future rewards, emphasizing that the reward today is worth more than the same reward tomorrow. Our neural network policy is parameterized by theta. We want to learn theta that maximizes the cumulative discounted reward. The update rule for theta is theta new is equal to theta old plus the learning rate alpha times gradient of the objective function. The key update rule in reinforce is that the gradient of the objective function is represented as shown in the second line. Expected value of gradient of log policy times the discounted rewards. The log pi is our policy and gt, and the sum is the sum of discounted rewards from time step t, where gamma is the discount factor between 0 and 1. Let's take a closer look at our policy network. It's a neural net that takes in a state as the input and outputs action probabilities via SoftMax function. We can see the layer definitions in the constructor and the forward pass in the forward function. Here we have a fully connected linear layer followed by dropout, followed by ReLU, followed by a second fully connected layer, and finally the SoftMax. This policy network is trained in a way to encourage actions that produce higher rewards and discourage actions that produce lower rewards. In this function, we compute the action probabilities given a state via forward pass through the policy network. Then we sample an action from the categorical random variable and save log probs from the sample action to be used in the loss computation later on. To update our policy, we need to compute the policy loss function. The policy loss consists of negative log prob times r, the discounted reward, accumulated over time steps. We use negative sign here because in our REL we want to maximize our rewards, while in PyTorch we want to minimize the loss. Once we have our loss computed, we zero the gradients, call loss.backward and optimizer.step to update the parameters. Finally, let's put together the different pieces we just looked at into the main loop. For each time step, inside an episode, we sample an action, interact with an environment, and receive a new state and the reward for taking the action, and then update the running reward. Finally, we call finish episode function that computes the policy update, and we repeat this process. Let's describe some of the pros and cons of reinforce and ways it can be improved. Pros is the algorithm is simple, it directly optimizes the policy, and works for continuous and discrete action spaces. Cons is that it leads to high variance gradients, has poor sampling efficiency, and training can be unstable. There are several ways to improve upon the cons. First is by introducing a baseline, by subtracting a baseline from the cumulative discounted rewards GT. If we choose the baseline to be the value function at state ST, we get an advantage estimate. Further, if we utilize TD learning, which stands for temporal difference learning, with the update as shown, we get the actor-critic algorithm. As you can see, reinforce is foundational to many modern RL policy gradient algorithms. Now let's take a look at PyTorch implementation of reinforce. So let's look at different pieces of code that we already talked about. Just note that this code is available in the video description below. Here we have our gym environment, which is the cart pole, the policy network, the optimizer, select action function, finish episode function, and the main loop. So let's run it and see how we could balance our cart pole. So there are two states that the cart pole, sorry, there are four states, but two actions that the cart pole can take, which is moving left and right in different coordinates. So we could see it's balancing so far. And here we see that the last reward was 18 and the average reward is 13.96. We could see as the number of episodes increases, the average reward is going up as well. Let's wait for one more output here. Yeah, so essentially we learn in a policy, right? So as the cart pole moves around, the policy network's been updated to maintain its vertical position. Hope you enjoyed this video. We covered one of the fundamental policy gradient algorithms in ReLU with complete implementation in PyTorch. If you have any questions, feel free to leave them in the comments below, and don't forget to like and subscribe. Thanks for watching.